In this video, we introduce planar graphs and we prove the Euler identity for planar graphs. So to start with, what's a planar graph? Planar graph is a graph that can be drawn in the plane without any two of its edges crossing. Such a drawing, when you've actually drawn a graph in the plane with no two edges crossing, is called an embedding of G in the plane, or a planar embedding of G. And a graph G that is already drawn in the plane, we call this a plane graph, with no two edges crossing, that is. So here's just to illustrate these definitions. So K2, as we saw before, this was a graph of a regular polyhedron. In particular, the octahedron. This is a planar graph. And I don't care how you draw it, no matter how you draw it, K2, just the graph object is a planar graph because it can be drawn in the plane, right? So I could draw this as with a planar embedding. So that is a drawing of the graph in the plane with no two edges crossing. So I can do this in the following way. Connect up like this. And there is the plane graph. It's drawn in the plane. We also call this, planar embedding. Embedding of K2. Now I'm going to actually blow up this drawing a little bit bigger here to illustrate what we can do when we have a planar embedding of the graph, when we actually have a plane graph. What we can do is we can recognize that the plane, once we have this drawn, is divided now into regions. Now, all but one of these regions is bounded. So here I'll call this one R1, R2, R3, R4, R5, R6, R7, and then the outside region R8. So the plane, right, think about the entire plane is divided up into these 8 regions once we have drawn this, this planar embedding of the graph. Right, so that's the idea. This is one thing we're going to want to keep track of are these regions. We'll want to keep track of how many regions there are and how many edges bound each region. So in this case, each region, including the exterior region, the unbounded region, is bounded by 3 edges, right? It's always going to be bounded, by some number of edges, and in this case, it's 3 edges. So this is what's meant by planar graph, plane graph, and planar embedding, and also how the regions are defined. All right, so let's take a look at a couple more examples here. And again, I want to keep track of number of vertices, number of edges, and the number of regions. So usually we let n be the number of vertices, right? The order of the graph. M, the number of edges, of course. And R, so a new parameter that we're going to look at the graph of, and this is only defined for a plane graph, is the number of regions. So here, G1, I can't really talk about the regions because I have crossings, so it's not clear how the regions here would be defined. So what we need to do first is give a planar embedding of the graph. So in this case, K4 that we have here is the tetrahedron, is the graph of the tetrahedron. And this is one way to draw it in the plane with no crossings. Now it's divided up into 4 regions. It has 4 vertices, 6 edges, and 4 regions. So notice Euler's polyhedra formula working here. N minus M plus R is equal to 2. All right, G2 here. So every graph I've looked at so far has been the graph of some polyhedra, but a planar graph need not be the graph of some polyhedron. For example, K23 here. So one, I need to think of a way to draw this in the plane with no crossings. One way I can do this is here I'm going to put K, or my 2 vertices in the partite set, and then the other 3 vertices in the partite set, and it'll look like this, right? This vertex to all of those 3, this vertex to all of those 3. This is K23. And now I have it divided up. Now I can count the number of regions. There's 1, 2, 3 regions. Let's see. So let's test Euler's formula here. Does it still work just in general for plane graphs? So n, I have 5 vertices. I have 1, 2, 3, 4, 5, 6 edges. And number of regions, I have 3 regions. N minus m, minus 1 plus r, that's 2. So this is kind of cool. We still have that Euler's formula is working, even though this is not a graph of any polyhedron. Finally, this one certainly is not a graph of any polyhedron. This one's a little bit different. Notice it's already drawn in the plane. I have one big outside region. I'll denote 1. Other regions I have 2, 3, 4, and 5 are my regions. And let's see. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices. N equal 9. M is equal to 12 edges. And how many? I have 5 regions. Yep, so again, Euler's formula checks out. N minus m plus r is equal to 2 here in this case as well. So it seems Euler's Euler's formula is going to work even for planar graphs that do not arise from polyhedra. Well, let's prove it. Let's use our knowledge of graph theory to actually prove this. So what we're going to do, proof, we're going to go by induction. We're going to use induction on the size of the plane graph. So as a base case would be when m is equal to 0. So there's only one graph, there's only one connected graph with 0 edges, and that's K1. So the base case is K1. It has n is equal to 1 vertex. It has 0 edges. And if I draw K1, it just looks like this. There is just one region, the exterior region. So n minus m plus r is 2 here, so the formula holds. Or the identity holds, however you want to say it. So now we're going to assume, so now for the induction hypothesis, so assume for an integer, positive integer m, that if G is a graph, maybe I'll say H. Yeah, I gotta follow the book. That if H is a graph with, and I'll use primes here, n prime vertices, r prime regions, and less edges than my integer m. So if H satisfies this as less edges than an integer m, then the formula holds. That is n prime minus m prime plus r prime is equal to 2. And so there's my induction hypothesis. And now I'll let G be a graph with m edges, n vertices, and r regions. So maybe I'll zoom in a little bit here. So, right. Two cases here. Case one, if G is a tree. We know G is connected, so it's possible it's a tree. If G is a tree, we're going to check that the formula holds. So think about what would happen if G was a tree. So I don't know, draw a tree as an example. Something like this. Well, how many regions will I have? Well, there's no cycles in the tree. And so the regions, I would just have one region. So my R would be equal to 1. And then I can't say I'm just doing this for any tree of size m, but I do know a relationship between n and m, right? N right. So let's say order n, and then its size m would be equal to n minus 1, right? We know it has one less edge than the order. And so if I do this, I would have n minus m plus r. So n minus m, so that's n minus 1 plus 1. Well, that's 2. Cool. So when G is a tree, the formula holds. Notice I did not have to invoke the induction hypothesis there, but this helps with the next step because now I can assume G is not a tree. Yeah, I think I'm going to go down to a new slide. So we know now we can assume G is not a tree and that any graph with less edges than it is has the formula hold. So case 2, G is not a tree. So what do we know about graphs that are not trees? Well, we know in a tree, every edge is a bridge and would disconnect the graph. If G is not a tree, then one of its edges is not a bridge. Then there exists E in edge set of G such that E is not a bridge. So E is not a bridge. That means it lies on some cycle of G. That means it's a boundary between two regions. So think about, I don't know if I have a situation, maybe something like this. Well, this edge is not, I guess think about any edge here is not a bridge. It lies on some cycle. If I pick any of these edges, it lies on the boundary of two regions, one region, two region. And so if I remove this edge, and this is what we want to do to invoke the induction hypothesis, when we remove the edge, we're going to take two regions and they're going to be combined into one region. So I'll have one less region than I started with and one less edge. And so it seems reasonable that the Euler, that the formula will hold then. So let me make this clear. In G minus E, two regions merge into one region. So G minus E, we didn't remove any vertices, has order n, size m minus 1, which is less than m, so my induction hypothesis will work, and r minus 1 regions. Since it has less edges, so by the induction hypothesis, it follows that n minus the number of edges, m minus 1, plus the number of regions, r minus 1, is equal to 2. That's what the induction hypothesis tells us, is that the formula holds, and then check it out. Now I have n minus m plus 1 plus r minus 1. The ones cancel off. I have n minus m plus r is equal to 2, which is what we wanted to prove. So that's pretty neat. We now have a proof that for any plane graph, number of vertices minus the number of edges plus the number of regions is equal to 2. Since any regular polyhedron gives rise to a plane graph, this is a generalization of Euler's polyhedron formula. So remember, he wasn't able to prove this in his first paper where he pointed this formula out. And even in his second attempt to prove this, it wasn't quite right. It was Legendre that eventually proved this, and it wasn't super pretty. Here we just proved it in, I don't know, a few minutes, 5 minutes or so. We were able to prove this result. It's not too bad. So the key thing here is that geometry used to be just a study of distances, and so people really weren't. They didn't have all this theory of this thing, that Euler called the geometry of position. This theory wasn't built up yet. Graph theory wasn't built up yet. Now that it's been built up, we have all these things we can talk about, like trees. We understand how the edges of a tree relate to its number of vertices. We're able to use all those facts and improve this really nice result that took other mathematicians a long time to do. So this is pretty neat. Now, one thing to note here is that if I have a disconnected plane graph, or just in general, if G is a plane graph, so think about a graph, I don't know, like this one, maybe it's K4 with another triangle, something like this. Maybe this is my graph G. So now for each one of these, I would have n minus m plus r is equal to 2. But now there's 2 connected components, and there's still only 1 exterior region. And so if I added things up here, I have 1 face, 2, 3, 4, 5 total regions. Number of vertices here, I would have 7. Number of edges, I have 3 and 6. I have 9. 7 minus 9, that's 2. Or negative 2 plus 5, that's 3. Doesn't add up. Doesn't give me n minus m plus r. N minus m plus r here is equal to 3. So why this isn't working is because they share this outside region. So the generalization here for just a plane graph that's not necessarily connected, it's 1 plus the number of components in the graph. That way, if it's connected, number of components is 1, and we recover the original formula. So here we've generalized it just a little bit further. Okay, that's it for this video. In the next video, we'll talk about identifying planar graphs, and in particular, an upper bound on the size of a planar graph. I'll see you there.